Right. Hello, everyone. Let's get started with this session. This particular session was supposed to be presented by Khalid Gohar, but unfortunately, he, for some personal reasons, cannot be here. So I have been tasked to look after this session. So I hope everything will be fine. So this is the last session of the day, the first day of the conference, and it's on wearable assistive devices. So for the benefit of the presenters, we have got a slot of 15 minutes for each presentation, of which the presenters will use 10 minutes to present their work. Then we will allow about 3 minutes for questions, and the remaining 2 minutes will be for the next presenter to get started. So the first presentation is paper number 26, and it's titled Simulation of a Walking Robot Exoskeleton, Movement on a Movable Base. And so I would invite the presenter of this particular paper.
Yes, thank you so much. I will show my okay. Can you see my desktop?
Yeah, I can see it.
Okay, so good afternoon, dear colleagues. My name is Andrei Malchikov, and I want to present my work. It's dedicated of simulation of walking robot exoskeleton movement on a mobile base. This work was carried out in Southwest State University. It's Kursk, Russia. Okay, and first of all, our motivation. Exoskeletal devices are widely used for rehabilitation of patients with disorders of the musculoskeletal system. And the maximum effect is achieved when the patient and the exoskeleton form an integrated human-machine system, the effectiveness of which is determined by the degree of synchronal motion of the elements of the system, including the human and active exoskeleton. In this case of the creating of rehabilitation complex, the task of studying walking on the mobile base, synchronizing the movement of a walking device and the moving surface is relevant. Within the framework of this investigation, mathematical model of the movement of exoskeletal executive units and algorithms of the motion control system are developed. And this slide, you can see our rehabilitation exoskeleton. Exolite is and the left side, it is a mobile version of our exoskeleton, and on the right, it is rehabilitation complex which we use in medical hospitals. Okay, in this slide, you can see general structural scheme. The upper parts of the exoskeleton is attached to the fixed base, the frame. The femoral links 2 for left leg and 4 for right leg by means of active joints that contain electric drives creating movements that can have a assisting effect on the patients are attached to the body. The task of the control system of the hip and knee joints actuators is to realize this relative motion of links, at which points OL3 and OR3 move along the desired trajectory, implementing a working motion of the exoskeleton. An important feature of the desired trajectory is to ensure that there is no slippage or impact at the moment of contact with the surface, which is provided by the choice of appropriate boundary conditions. In this slide, you can see equation for forward kinematic and inverse kinematic when we used in our mathematical model. Here, next step is trajectory planning. The trajectories of point OL3 and OR3 are determined by the parameters of mechanism, type of gate, and step parameters. Let us introduce a coefficient K epsilon that determines the shape of trajectory. In this equation, epsilon F is the speed along the linear part of the trajectory, its movement together with the support surface, and epsilon B is the maximum foot speed for symmetrical walking. Using the coefficient, we can obtain a vector of gate parameter S. Here S is the step length, H, small h is the height of a leg when walking, capital H, the distance from the hip joint to the treadmill running, and TS, the duration of one step. For trajectory, convenient to use a piecewise polynomial function. Coefficients of polynomial function determined by this equation, which use initial time, final time of fragments, and coordinates and its speed values. Since the trajectory is symmetrical, it can be split in 3 fragments, A, B, B, D, and DA. Boundary conditions for fragments are shown on slide. Here we can see equation which we used for mathematical modeling this algorithm. This is example trajectories. We setting the step parameters values. It becomes possible to obtain different trajectories of the point O. As shown in the graphics, we developed trajectory planning algorithm allows obtaining a continuous trajectory for multiply step parameters. Using the trajectory shape coefficient K epsilon, possible to obtain the required law of moment of length. This law is necessary to establish the parameters of mechanotherapy of a specific patient, which simplifies the configuration and preparation of equipment for each patient. Next, we can see the result of numerical simulation. Unfortunately, I can't see the animation. And on this slide, we can see just frames of animation and different times of modeling. Next slide, you can see the result of the graphics of simulation. Its laws of change of the coordinates and trajectory performing. It is what we desire. Here, it's laws of change the absolute angles. And finally, we have laws of change the relative angles. These graphs, these data we use in our prototypes for our trajectory. Next, it's conclusions. During investigation, a mathematical model of the moment of a two-legged walking mechanism on a mobile base of treadmill has been carried out. A method for studying this mechanism has been proposed. Also, trajectory planning algorithms have been developed, and as well as the equation for solving the inverse kinematics problem for the mechanism links have been written. In order to set the shape of trajectory, a coefficient K epsilon is proposed. The presented method is proved by mathematical modeling, which demonstrates the applicability and appropriate operation of the developed algorithms for trajectory planning for robot-exoskeleton device. The result of this work we use in our experimental for our prototypes. Thank you for your attention.
Ну, если дадут такую возможность, если дадут такую возможность, задам.
Да, пожалуйста.
I'm sorry, I'm Nikolai Bolotnik. I want to ask you whether you used only kinematic model, or did you involve also dynamic equations when simulating?
Thank you for question. In this framework of this work, we use only kinematics because the main idea of this work is to determine the law of change relative angles for prototypes, but also we have dynamic models when we modeling different dynamic control system. For control system, we modeling control system. We determine dynamic parameters for motors, for design the construction of links and so on. But in framework of this work, we only kinematic scheme investigate.
Thank you.
Any question?
I will ask you another question. At the beginning of your presentation, you showed two types of exoskeletons. Were these exoskeletons implemented physically, or is it only a conceptual design, a conceptual model?
Okay. On this slide, on this photo, we can see a real prototype. We use it with real patients, but it's not. We have no clinical. I'm sorry, I don't know how it in English. We can use it in medical, in hospitals, because it's not клинические испытания, как это сказать? Прошу прощения.
Clinical tests. Clinical
Yes.
tests, clinical experiments.
Yes, it's a real prototype. It's work. It's developed in our laboratory. We use it with patients with problems, and it works. But we need more investigation in this work. For example, it's a simulation of movement on mobile base. Because in the right side, this slide, you can see the complex which use the small wheels on the legs for providing sliding between the exoskeleton and floor. And our next step, our future work, is the use the treadmill running. And for this, we investigate this question with walking on the mobile base.
Okay.
Thank you.
Thank you very much.
Thank you.
We've got 1 more minute actually for this, but I'll ask the next presenter to get ready. But while we are, I wanted actually to ask you also a question, if you don't mind, on the trajectories which you have tested. Were these trajectories generated randomly, or were they based on certain type of measurements?
we use the measurement system for investigate trajectories of the real human, and for this we try to calculate the same trajectories, and this mathematical model, these algorithms can be useful for this trajectory.
Okay, thank you very much. Thank you very much for the presentation. So I think we will give the floor to the next presenter.